Hello there! This video is going to give you all the basic information that you need to interpret statistical and practical significance of research results. So if you see this sampling distribution is from the Statistics Survival Guide that I published on Top Hat. And basically what we are thinking about is the analysis behind the research results that we're reading in journal articles. And where do these significant findings come from and what does they mean? And in general, it means that it is very unlikely that your results would have happened due to random chance. So if you look, this entire sampling distribution is a hypothetical distribution, and it represents all the possible results that you would have gotten due to sampling error, or if the null hypothesis, which states that nothing is significant, is true. And so when we are doing research, we are hoping that our outcome is highly unlikely, that it falls in one of these extremely unlikely ends of the distribution, because remember, taller areas of the graph, like here, represent more probable outcomes, right? So it's more likely, right, more probable to have an outcome that's kind of close to what you would have seen in the population. But if your outcome is unlikely to have come from that population, it falls out in these tail ends of the distribution, has a low p-value, as you see here, and then we can say that there's a low probability that the results happened due to random chance, happened due to sampling error, which means that we can be confident that the results that we got represent a true effect of the independent variable on the dependent variable and weren't something that happened due to a fluke. If that's still confusing for you, that's okay, because I'll break it down a little bit more here in a minute. So next, I'm just going to give you a quick recap of the scientific method and the variables used in research, then looking at what statistical significance means, and again, tying it back to those p-values, those probability values, and then looking at practical significance through measures of effect size. So when we think about the scientific method and the process of writing a research manuscript and doing research, we are really focused on this section right here, section 4. We are looking at how researchers, after they have their data, they've collected their results, how they report those, and how they interpret their test hypotheses and whether or not they were supported by the research or not. So we're really focused right now on looking at the results of research. So if you remember from a previous video, we've got independent variables, quasi-independent variables, and dependent variables in research. Independent variables are manipulated causes based on, past theory and research. And you'll see those in experimental or quasi-experimental research where conditions are actually manipulated. Quasi-independent variables are measured, and they are like the supposed cause based on past theory and research and the relationship that you're looking at in your hypothesis. But we usually call them predictors because when we have quasi-independent variables, when we're doing correlational or non-experimental research, we don't really say that there's causal effects there. Then remember, the dependent variable is always the variable that depends on the independent or quasi-independent variable, and it's almost always measured. So when we're looking at dependent variables in an experiment, we usually call them an effect. When we're looking at dependent variables in a quasi-experiment, we usually refer to those as an outcome. And when we're looking at dependent variables in a correlational study, we usually refer to those as a criterion. But I'll probably use them interchangeably. So now let's think about some examples of independent or quasi-independent variables and dependent variables. And I know it's tricky because quasi-independent variables aren't involved in quasi-experimental research. Sorry about that. That's not my fault, but I know that's tricky. So try to kind of, put those two things apart, right? Quasi-experimental research involves manipulation. Correlational and non-experimental research don't involve manipulation, and that's why the independent variables and that type of research is called a quasi-experiment. So here's an example. So I'm also going to mention the modality measurement and type of study here so that you can really review things we've already covered. So let's say that a researcher thinks that small groups will be more cohesive than large groups. So they conduct an experiment where they randomly assign research subjects to solve a challenging problem in either a large group or a small group, and then they measure differences in cohesion. So here we have an independent variable, which is group size, and it was manipulated. And we have two conditions. we have the small and the large group. And those are on an ordinal scale because they're not truly numeric, but small is smaller and large is larger. So there is some order there. Then our dependent variable, or the effect, is the level of cohesion. And this is measured or operationalized through self-report surveys, probably empirically validated multi-item survey measures that are on a Likert scale. So this could also, you could measure cohesion through observation of group interactions as well. So you could maybe look at the frequency of some predetermined behaviors that indicate the level of cohesion. Like you could watch the groups work and record the number of agreeable statements they make to each other, the number of compromises they make, and the number of decisions made. So that would be an experimental study. Another example would be a researcher that wants to do non-experimental research to maybe see if older students will be more eager to do collaborative learning and group projects than younger students. So here your quasi-independent variable is age, and it's a self-reported ratio variable because it's truly numeric and there's no negatives possible. So it has a true 0 point. The dependent variable in the study would be positive attitudes and eagerness to do group work. And you could measure or operationalize that through self-report surveys. So again, probably using empirically validated multi-item surveys measured on an interval or Likert scale. Or you could measure or operationalize eagerness for group work through observation. So maybe research participants are given a challenging task and then are given the option to work in a group or work solo. And you record differences in age between those who wanted to work in a group and those who opted to work solo. So that would be a non-experimental research example that uses a quasi-independent variable and a dependent variable. When researchers are examining the differences in dependent variables based on independent variables, or the relationships between quasi-independent variables and dependent variables, they must plug the data for their measures and or their conditions into a statistical analysis. And the purpose of the analysis is to aggregate all the data into a summary of trends and results. And for researchers to be confident in any of their observed differences or relationships and trends among their variables, results typically need to be, quote, statistically significant. I'm sure you've heard that phrase before, but I want to make sure that you understand it now. So statistical significance is really looking at, is there a reliable difference between groups or a reliable relationship between variables? Results with a low probability of occurring due to random chance or sampling error are said to be statistically significant. Results that are unlikely to be observed if the independent variable has no effect on the dependent variable, which is basically the same as saying it's unlikely that we would have seen this due to random chance, again tells you you have a statistically significant effect, that there is statistical significance there. That's what it means. So if you think about it, if the results aren't due to chance, right, they're not due to some fluke sampling error or pre-existing differences or some other random noise, and results suggest that the independent variable actually does have an effect on the dependent variable, right, because it's unlikely that it's just due to chance, then the results that you observe in the sample would likely be observed in the population, because the independent variable actually does have an effect or relationship with the dependent variable. So when we talk about probabilities and how likely things are, we're really focused on p-values. And in statistics and in research, we love low p-values. We want to see that p less than 0.05 or p less than 0.01. And what that basically says, if your p is less than 0.05, it means that there is less than a 5% chance that your results occurred to some random chance sampling error. In other words, there's less than a 5% chance that you got your results even if the independent variable had no effect or relationship with the dependent variable. So really, the p-value is the decision maker for statistical significance. In research, we're usually willing to accept a 5% chance of type 1 error. So that's why our standard is kind of p equals 0.05 or lower, and that's called an alpha level. You don't really need to know that. That's kind of stats nerd for you. But that's kind of what our standard is. We're willing to accept a 5% chance of concluding that something had a reliable effect, even if it didn't. And if the probability that happened is even lower than 5%, then we're even more excited and more confident in our findings. So again, that p-value tells you the probability that the observed difference between groups or the relationships between variables would have occurred due to random chance sampling error, or in other words, the likelihood of obtaining your study results if the independent variable doesn't have an effect on the dependent variable. So if the P is low, we can reject the null hypothesis and say there's a low probability that our results are garbage, so there's a high probability that our independent variable was related to or predictive of our dependent variable. So now I'm going to take some time to show you some examples of p-values and statistical significance in published research. So here's a summary of results from my article titled Insecurity in the Ivory Tower, the Direct and Indirect Impact of Budget Cuts, Pay Stagnation and Job Insecurity on Faculty Performance. That was published in the Economic and Industrial Democracy Journal in 2020. So take a look at the stars in the table. See those numbers with stars, and those are correlation coefficients. You know, you see your mean there, your standard deviation, and then those 1, 2, 3, 4. That corresponds to the variables on the left, and we're looking at a correlation table here. And just as a refresher, remember, to read a correlation table, you kind of find where two variables cross, and then kind of look at that relationship. So you can see here, variable 2 is pay stagnation, variable 1 is job insecurity. And so this 0.17 tells you the correlation between job insecurity levels and pay stagnation, or, you know, having your pay not increase over time. So if you see where the stars down here, that tells you that if you see 1 star, that means that P is less than 0.05. There's less than a 5% chance that that observed relationship is a fluke or is due to sampling error. If you see 2 stars, we're even more confident in those findings because there's less than a 1% chance that the observed relationship or correlation is just due to sampling error. And you can see that across the board for variable 1, job insecurity, right, this whole column here, that higher levels of job insecurity are significantly or reliably related to all the other variables in the study. And if you remember that positive correlation means that those with higher levels of one variable tend to have higher levels of the other variable, or those who have lower levels of the variable tend to have lower levels of the other variable, right? A consistent direction. Or negative correlations, right? Where higher levels of one variable are related to lower levels of the other variable. There's an inverse relationship. Then you can interpret these reliable, statistically significant correlations. And you can see that higher levels of job insecurity are significantly or reliably related to higher levels of pay stagnation and lower levels of job satisfaction and performance. Results also suggest that tenured faculty tend to have significantly less job insecurity, and I know that because tenure status was coded so that a higher number indicated a tenured faculty member. Just keep in mind, we're looking for all those stars to see which results were statistically significant. If we look at this negative 0.09 here, it doesn't have a star. So that means that there's not a reliable relationship between variable 2, pay stagnation, and what represents this row, performance. Here's another example from another correlational research project I worked on that was titled WIME, the Frog Pond Effect, Relative Deprivation and Individual Outcomes in the Face of Budget Cuts. And this was published in Work and Stress in 2014. So see the stars in the structural equation model. You see one right there. And look, down at the bottom, this tells you that if you see a star, that means there's less than a 1% chance, less than a 1% probability that the results are not reliable, that they're due to a random fluke. So that means if you see a star, it means results are statistically significant. So if you look at the stars in the structural equation model, you'll see that we have 2 different sets of scores for each relationship there. And that's because the non-parenthetical coefficient is for tenured faculty, and then the coefficient in the parentheses is for non-tenured faculty. And these are not correlations, they're structural equation coefficients for regression analysis, but they can be interpreted largely in the same way. So if you take a look at this, we can be confident that lower levels of job insecurity and pay stagnation have a reliable or significant relationship with higher levels of job satisfaction, which then predicts higher levels of performance ratings for tenured faculty. But among the non-tenured faculty, we don't see as many stars, right? Because remember, the non-tenured faculty is represented by the parentheses. And so there you see that among those non-tenured faculty, the only significant relationship is between pay stagnation and job satisfaction. So if the probability, the p-value, that results are due to sampling error is low, right? P less than usually 0.05 is our standard. And you conclude that the dependent variable is significantly different across levels of an independent variable, or that an independent variable and dependent variable have a significant relationship. This really only suggests that the observed differences or relationships are reliable. However, statistical significance is not the same as practical significance. In fact, it is quite likely that you will get statistically significant results with huge samples, even if the effects of the independent variable on the dependent variable are minuscule, or the relationship between those variables is really weak. The effect size tells you the absolute magnitude of an independent or quasi-independent variable's effect or relationship on the dependent variable. And it does it regardless of the sample size, because it's very easy to get significant results when you have a large sample size. So the effect size is a measure of practical significance that's really important to consider once your results are statistically significant. So some really popular measures of effect size are Cohen's d, r-squared, and eta-squared. And Cohen's d is used when you're examining the differences in a dependent variable across conditions or levels of an independent variable. And it can be evaluated with the table that you see here. So you look at your, if your Cohen's d value is close to 0.20, or in other words, between like 0.00 and 0.35, that's a small effect, and so on up to a very large effect. R-squared, my personal favorite, or eta-squared, is used when you're examining the relationship between quasi-independent variables and dependent variables. And R-squared can be evaluated with the table that you see here, but it's really evaluated like a percentage. Specifically, R-squared tells you what proportion or percentage of all the differences or variability in your dependent variable that's due to or predicted by the quasi-independent variable. So for example, if we had an R-squared of 0.116 in a study where we were looking at the relationship between age and eagerness for group work, we could conclude with that 0.16 R-squared that 16% of the differences in ratings of eagerness for group work were predicted by age, and 84% of the differences in eagerness for group work are predicted by variables other than age, like past experience with group work or social anxiety. So this is a moderate effect. Ideally, the researcher would have also measured those variables like past experiences with group work and social anxiety and controlled for them statistically in the analysis to see how well age predicts eagerness for group work, even after controlling for those extraneous variables that may influence the attitudes and perceptions about group work. So you can see that most of our pie isn't being predicted by our study, but we're still pretty excited about predicting 16% of the variance in our dependent variable with just one quasi-independent variable in our analysis. So I'm going to come after my own research for a minute. You'll notice, as before, all of the relationships with our variables and job insecurity were statistically significant. They were reliable. We were confident that there was a true relationship there. But that doesn't necessarily mean that is a strong relationship, that is a strong effect. In fact, much to my chagrin, all of my effect sizes here were pretty small. They were pretty weak. Granted, it's still cool to be able to predict 3% of the differences in job insecurity based on pay stagnation, or predict 12% of the differences in job insecurity based on tenure status. But it's still, we have a lot of other variables that we needed to look for. And we actually did a more sophisticated analysis where we kind of parsed out the variability and controlled for other things, but I don't want to show that here. But as you can see, even though my findings were statistically significant, the practical significance was not as exciting. So please keep that in mind when you're looking at results, especially results from correlational studies. So I hope that you feel ready to read journal articles and results sections and think more carefully about what it really means when somebody says that findings are statistically significant. Remember to consider the effect size, because large samples usually give you statistical significance, even if the relationships or differences are tiny.